The concept of infinity has captivated mathematicians, physicists, and philosophers for centuries, while mathematics rigorously defines infinity through Cantor's hierarchies of infinite sets or calculus's limits approaching boundless values. We must question whether infinity physically exists in nature or remains merely a useful abstraction. This exploration examines infinity's role across physics, cosmology, and philosophy, ultimately arguing that while infinity serves as a powerful mathematical tool, it likely has no genuine place in our physical universe. Mathematics employs infinity as an indispensable construct with profound elegance. Cantor demonstrated how some infinities surpass others in size. Uncountably infinite real numbers dwarf countably infinite natural numbers, while calculus uses limits approaching infinity to model continuous change. Fractal structures like the Mandelbrot set reveal infinite complexity within finite boundaries, creating breathtaking mathematical landscapes. Yet, mathematical utility doesn't guarantee physical reality, much like how perfectly straight lines exist in geometry but not in nature's curved spacetime. Infinity might be purely conceptual. The relationship between physics and infinity proves consistently problematic, revealing nature's apparent preference for finite structures. Classical physics faced the embarrassing ultraviolet catastrophe, predicting that heated objects should emit infinite energy at high frequencies. Quantum mechanics solved this by introducing discrete energy quanta. This quantum revolution suggested that nature operates in finite chunks rather than smooth continuums. Quantum field theory later encountered infinities in particle interactions, requiring renormalization techniques that even Dirac saw these infinities as a red flag, a sign that our theories were incomplete. The math worked, but it felt like a magic trick. It gave us answers without really explaining what was going on. Einstein's general relativity predicts black hole singularities with infinite density and curvature. Yet most physicists view these mathematical monsters as signaling theoretical breakdown rather than physical truth. The measurement problem in quantum mechanics raises similar questions. Does a particle truly exist in infinitely many superposed states before measurement, or is this mathematical convenience masquerading as reality? Even cosmological models proposing infinite universes remain fundamentally unverifiable since we observe only finite regions bounded by our cosmic horizon, leaving infinity's existence tantalizingly uncertain. Contemporary physics increasingly suggests nature's discrete character eliminates infinity at fundamental levels. At Planck scales, spacetime may become pixelated rather than continuous, preventing infinitesimal divisions and creating a cosmic resolution limit. The holographic principle proposes that any region's information content is finite, encoded on its boundary like a cosmic hard drive with limited storage capacity, implying reality itself might be fundamentally digital. Loop quantum gravity attempts to replace Big Bang's singularities with finite bounces, suggesting even the universe's birth involved no infinities. As physicist Gerald Tufte observes, infinities appear to be artifacts of our ignorance rather than genuine features of nature. These scientific developments carry profound philosophical implications that challenge our understanding of mathematics' relationship to reality. If infinity isn't actually out there in the universe, then math isn't some eternal truth waiting to be discovered. It's more like a language we created to make sense of things. Some physicists like Lee Smolin advocate finitism, proposing the universe is fundamentally finite and quantized. Compelling evidence suggests nature inherently avoids infinity. When infinite values appear in physical theories, they typically indicate model limitations, like treating electrons as point particles when they may have finite structure. The cosmic microwave background's isotropy, sometimes cited as evidence for infinite space, could equally result from finite but very large universes beyond our observational horizon. In the end, the evidence points clearly. Infinity is a powerful mathematical idea, not a physical truth. Nature works in finite, discrete steps, from quantum energy jumps to the fabric of spacetime itself. When infinities appear in our theories, they are not revelation of reality, but red flags exposing gaps in our knowledge. The quest to vanish these infinities isn't just technical, it's a profound push toward a deeper vision of the cosmos. As Einstein suspected, we may live in a universe where true infinities has no home. Yet this very limitation opens doors to richer understanding. In bridging math and physics, we are not just solving equations, we are decoding the finite heartbeat of existence. Thanks for watching. If you found this video helpful, give it a thumbs up and don't forget to subscribe to the channel.